Now, we are talking about the molecular orbital theory in last class. So it's like that. So we have two hydrogen atom, this is a hydrogen atom, this is another hydrogen atom. This has one electron, this has one electron. And how they make a bond according to molecular orbital theory is, so this guy, this electron is waving like this, and this electron is also waving like this. So the peak is combined just below this peak. This peak is just below this peak, and this peak is just below this peak. So there are these electron waving like this. Therefore, they form this bond. So the probability of finding those electrons is higher between the nucleus of these two hydrogen atoms. Yeah. So that's how they form the bond. And this electron may be waving like different way. So one electron of this guy is waving like this, and then the electron of this guy may be waving like this. So they're canceling each other. Make sense? You see that the peak is going up this way, this peak is going down, this peak is down, this peak is up. So these two waves are interfering to cancel each other. So if you want to represent this is like this. This is the s orbital of this hydrogen, this guy. The s orbital of this hydrogen is this one. So that is one, we call one SA, and this electron is from this hydrogen, and then that is one SD. So these two electrons are represented like this way. Yeah. And if you want to represent this one, this is represented like 1SA minus 1SB. Why? They are canceling each other. The peak is here is pointing up, the peak is pointing down. Here the peak is pointing up, peak is pointing down. So they are canceling each other here. They are not canceling each other. They are just combining to give high intensity amplitude wave here. So this is called constructive interference, constructive interference of wave. This is called destructive interference of wave. Destructive interference of wave. Interference of wave. So this gives, these are two electrons. You see here, these are two electrons, and these are also two electrons. Yeah, sometimes here is one electron, there is two electron. Sometimes two electron here, one electron here, sometimes one electron here, one electron here. So we'll look those kind of thing later. So this one is called bonding anti-bonding molecular orbital. Anti-bonding molecular orbital. Why? Because they are destroying each other. So the electron don't want to sit here. If the electrons sit here, they don't want to give the bond. But here the electrons are sitting in internuclear axis, and they try to bind hydrogen and hydrogen together. So this is called molecular orbital bonding. So this is molecular bonding molecular orbital, and here is anti-bonding molecular orbital. Make sense? So like that. So how we write this in this book is like this. So let's say we have the one s orbital here of hydrogen, and this is another one is this is from another hydrogen atom. So they are interfering constructively. So they say, okay, so let's represent this like that. Make sense? So this is this is a nucleus of one hydrogen, this is the nucleus of another hydrogen, and this orbital and this orbital are constructively interfering one over another, and here it looks like this. So if the one electron is here, one electron is here, so those electrons come here and sit like this. This is bonding molecular orbital. It's exactly like how I wrote like this. So this is like this. So there is a high probability of finding this electron in the internuclear axis. Make sense? Good. Now the bonding is represented like this. How about the anti-bonding? So let's say here is a 1s and here is a 1s of hydrogen atom again. So this is 1s orbital, this is 1s orbital, and if they combine together, they destructively combine. Destructively combine means, so this is like this, and this is like this, and there is a node. There is no probability of finding electron in between these orbitals. Make sense? So this is a destructive interference. You see, here these two lobes, this lobe and this are just overlapping each other and making this bonding molecular orbital. Bonding molecular orbital. And this is called anti-bonding molecular orbital. So this makes the system stable, this makes the system destable. Make sense? So you see, there is an open space here in between this one and this one. There is an empty space here. This is called node. N-O-D-E, node. Node means we cannot find the electron in between the internuclear axis right here. Make sense? So if the electrons are there, maybe they are just one is moving this way, one is moving this way, so like that. So this is anti-bonding molecular orbital. In our book, we don't draw something like this. We draw even simpler. So this one is drawn as a line, and this is also drawn as a line. So in the next one, I'm going to show that one. So let's go to the slide number 13. So let's go to the slide number 13. So in slide number 13, we are showing the hydrogen molecule here, hydrogen molecule. So no matter where you go in higher level, you go to the master, PhD, you took a higher level course, they always start from the hydrogen, and they teach exclusively hydrogen atom, and they don't teach other things that much because other things are so complicated. So everybody loves to talk about hydrogen because it is the most simplest molecule. Yeah. So like this one. Now let's write the hydrogen this way. So this is a hydrogen atom here. This is hydrogen atom here. So if you look the electronic configuration of hydrogen, this is 1s1, right? 1s1. That has one electron. So this is, so we just write like this. So this hydrogen. So this is a hydrogen atomic orbital. We write this hydrogen atomic orbital. We just write the line here. We don't draw a spherical orbital here, just to make things easy. Yeah. But it is always spherical, but we don't use spherical, so we just draw the line. So this is 1s1 orbital. So this is 1s orbital, and there is one electron. Make sense? So this guy. So this guy is this one. Make sense? So we are just trying to simplify things. And there is another hydrogen atom. These are same energy level. So this line and this line in the same level. This is called energy. This is, if you see, the energy is increasing in this hydrogen atom. This is 1s orbital, and this is the hydrogen atomic orbital. And let's write another hydrogen atom here. This is also hydrogen atomic orbital. Another hydrogen. This is one hydrogen. This is another hydrogen. Another hydrogen has also one electron in 1s. Make sense? Now we combine this orbital with this orbital, and then produce like this, right? So the energy of this one is lower than this, lower than this. So we just write here like this. This line is representing this one. So that's a bonding molecular orbital. Make sense? And then, so they are constructively combining here like this, and so we represent this as like this one here. Yeah, and they are also these two are maybe destructively interfering like this, right? And then we put those. Here is a anti-bonding. So this is this one, this is this one. So this guy is like this guy is like this. Make sense? Yeah, easy, right? But you don't have to understand these things here. So they are not important. Now, I told you, so where is it coming from? It is coming from this guy interfering with this guy, right? So we just draw a line like this. Okay, so this one and this one are interacting and giving this one. Next. And then this one and this one destructively interfering and giving this one. So we just give like this. Make sense? So what does this mean? That this electron is a wave, this electron is a wave, and they are constructively interfering here and giving this line here. That's what I am telling. Make sense? Good. So this one. And then here they may be like this one and like this. This one is this one. So there, these two electrons at wave function, whatever they call, they are destructively interfering and giving that one. Yeah. So we call this as a sigma molecular orbital. So this is bonding. So this is bonding energy. If you look the energy of the atomic orbital was high here, right? You see here, the energy of the atomic orbital was like this, yeah, high. But the energy of bonding molecular orbital is low. The energy is here, low, right? But the energy of the anti-bonding molecular orbital is higher than atomic orbital. Okay? So this is called sigma molecular bonding molecular orbital, sigma bonding, bonding bonding molecular orbital, and this is called sigma star anti-bonding bonding molecular orbital. Make sense? Simple. Now, this is one orbital. So they combine and they give one orbital here. So one orbital have maximum how many electrons? 2 electrons, right? So one orbital can have maximum 2 electrons. So this electron comes here and sit here, and this electron comes here and sit pointing downward like this. Make sense? So this is one orbital. So one orbital can have 2 electrons. So I put 2 electrons here. So I have only 2 electrons. 1, 2 electrons. There are no electrons to put here, right? So that's empty. Make sense? Now, with the help of this one, we can tell a lot of story about this hydrogen molecule. So what is the bond order? B-O-N-D bond, O-R-D-E-R border. How many bond order? How many bond form between hydrogen atoms? So this is hydrogen, this is hydrogen. So there is a one hydrogen, there is a one bond between this hydrogen molecule. So that is calculated as bond order. Let's see how many bond order in hydrogen. Bond order in hydrogen is, so count the number of electron in bonding and count the number of electron in anti-bonding and then divide by 2. So that is number of bond order. Electron is in bonding. So bonding, electron in bonding is 2, electron in anti-bonding is 0. And then you divide by 2. So that is 2 by 2 is equals to 1. So hydrogen, the bond order of hydrogen is 1. So if the hydrogen and hydrogen atom come together and sit together, the bond between them is 1. Make sense? That's called bond order. Now, this is the bond order. Now, another is a magnetic property. Magnetic property of hydrogen. Let's look at the magnetic property of hydrogen. So, is there any unpaired electron in this molecule? So this is a molecule, this is atom. I am not talking about atom and atom. Atom, if you see the hydrogen atom, it has one unpaired electron. So this is attracted toward the magnet if we hang near the magnet. So this is a paramagnetic. Hydrogen atom is paramagnetic. Hydrogen atom is paramagnetic. But if you look at the hydrogen molecule, there are no unpaired electron here, right? Both are paired. So this is diamagnetic. Make sense? So both in molecules, there are no unpaired electrons. There are no unpaired electron in E means electron. There are no unpaired electron in this bonding place, right? This molecular orbital. So this is diamagnetic molecule. Diamagnetic. So the greatest success of the molecular orbital theory is to tell about the bonding and the diamagnetic or paramagnetic and explaining the color. So if you have already done the experiment in lab number 12 or 11, I think the color, right? The color cobalt chloride. So why color comes in some molecule is explained by the bonding. This theory, molecular orbital theory. So in exam, I will put something like this. So I give the molecular orbital of the drawing or something like this, and I ask, is this molecule paramagnetic or is this molecule diamagnetic? Is this molecule stable or is it not stable? What is the bond order or something like this? Make sense? Good. So you can easily say our bond order is 1 in hydrogen because there are 2 electrons, there are no electrons here, so I get this one and 1. So this is a stable molecule. And I look here. I'm not looking here, I'm not looking here, I'm looking here in this molecular orbitals, and I'm saying, are there electron, all electron paired? Yes, all electron paired. Therefore, this is a diamagnetic molecule. So meaning that if you put the hydrogen molecules in hydrogen molecules, H2 molecules in test tube and hang here and put a very big magnet here, this is a magnet, so they will be repelled. This test tube will be repelled. Make sense? It's a diamagnetic. But if you put hydrogen atom, so this is hydrogen atom, just the H. So you hang here and big magnet here, this is paramagnetic and pull toward this way because it has unpaired electron here. Make sense? So these are for the hydrogen atom, these are for hydrogen atom, these are for hydrogen molecule. So this is for hydrogen molecule. Make sense? So easy. So if you understand this one, all is, I'm just repeating everything just like this one. Now, let's look the slide number 14. So this kind of the drawing is called the ground state. So I just did the ground state. In 13, I'm doing the excited state. So I have a one hydrogen atom here. I have one hydrogen atom here in the same level. So hydrogen atomic orbital energy, hydrogen atomic orbital here. So one electron here, one electron here. So they wave and constructively interfere here. They wave and destructively interfere here. So like this, and then so this one, now I'm doing the excited state. Previously I told that I have a hydrogen molecule and it is in the ground state, meaning that it's from there and it didn't absorb energy and sitting there doing nothing, right? Ground state. So now I'm going to do the excited state. So I have previously, so this is a molecular orbital. So this is sigma bonding, this is bonding, this is anti-bonding. So it is anti-bonding, so this is bonding. Sometimes they write the sigma here and sigma star here. Anti-bonding, they give the sigma star, yeah? Now like that. And how many electron I have here? So I put it one here, I put it one here, like this. So this is not excited state, this is a ground state. They form the bond and you sit there. They have not absorbed the energy. Make sense? Now, if you put this hydrogen molecule, so this is hydrogen molecule, right? Molecular orbital. This is hydrogen molecule. So this is hydrogen atom, this is hydrogen atom. What happens if I give the energy here? If I give the energy here, meaning that I have a hydrogen molecule here, now I give a lot of energy here, I heat it, and then the hydrogen molecule absorb energy, and this electron jump here. From this here, the electron jump here, one electron jump here. So this is called excited state. Make sense? So previously I show you the ground state, now I show you the excited state. The hydrogen is excited, it absorbs energy and it becomes excited, right? One electron jump up. Now let's calculate the bond order here. Bond order in excited state. BOND, bond order in excited state. So bond order is calculated at number of electron in bonding orbital here 1 minus number of electron in anti-bonding molecular orbital and divide by 2. So that is 1 minus 1 is 0, 0 by 2 is 0. So in excited state, you see in excited state, this hydrogen has one electron this way, one electron, they don't bond, there is zero bond. They don't bond in excited state. So the hydrogen molecule just break to give atoms. Make sense? Good? Any question? I think it's pretty easy. So in excited state, if the hydrogen atom absorbs a lot of energy, the hydrogen molecule break because there is one electron in molecular, this bonding molecular orbital, this one electron in anti-bonding molecular orbital. So this destabilizes the system. This try to stabilize the system. So they cancel each other. So their total value cancel each other, and the molecule just break. Make sense? Good. So this is excited state. So in excited state, hydrogen cannot remain as hydrogen. It cannot remain as like this. In excited state, just break and it forms hydrogen atom like this. Good. Alright. Now it's pretty simple there. Now let's look slide number 15. In slide number 15, why doesn't He2 exist? So like this. So let's look He. If you look at the chemistry book, you will see He, you will see H2, you will see He, but you never see He2. You never see He2. Why does this? Why doesn't this exist? So let's explain with the molecular bonding theory, molecular orbital. So the helium has it's a number 2. So its electronic configuration is 1s2, right? Make sense? So 1s2. Now put one He here. So this is one He, helium atom. So this is helium atom. In the same level, we are going to draw the another helium. So this is 1s atomic orbital of helium atom. This is also 1s. So this is also 1s. This is also 1s of helium atom. Now you are just doing constructive interference and destructive interference of those orbitals and going to produce the bonding and anti-bonding. So this guy interfere with this guy and give bonding molecular orbital here. And this guy also destructively interfere and produce this one like this. Make sense? So this is coming from the like this, and this is coming from the like this, right? Destructive. So this is destructive, this is constructive. So now, how many electron this one is guy have in this helium? There are two. There are two. And how many here? There are two, right? Now I have total of 4 electrons. So I can put, this is one orbital, this is one orbital. In one orbital, I can put only 2, not more than 2, right? This is one orbital, this is one orbital. So I can put 2 here. Now this is anti-bonding, so this is bonding. Sorry, this is bonding. So this try to stabilize the system. These 2 electrons try to make the He like this, and these 2 try to break this He and helium atom. Make sense? So let's calculate the bond order, or how many bond form between He and He if we do that. So bond order is BO. Bond order is equals to number of electron in bonding is 2 minus number of electron in anti-bonding is 2. I divide by 2. So the 2 minus 2 is 0. 0. So you never see there is a 0 bond between He and He. Make sense? So you never see He2 because there is no possibility of the bonding between He and He. Make sense? Sure. I will be putting something like this in exam. Yeah. Does He exist or does not exist? Why it doesn't exist? Because He has sigma bonding orbital and anti-bonding orbital. Bonding has 2 electron, anti-bonding has 2 electron, and 2 minus 2 by 2 is 0. And so there is no possibility of formation of the bond between He and He, right? So therefore He doesn't exist. Good. Now let's go to the slide number 16. So slide number 16. If you look now we will talk about, in this course we talk about hydrogen, helium, boron, carbon, nitrogen, oxygen, and fluorine, and other. So only we are studying this many molecules in this class. Yeah. So so we already finished hydrogen and helium. Now I'm going to talk about the boron. Yeah. Now let's look the boron. So now let's look the boron, carbon, and nitrogen. Three things behave one way, and oxygen and fluorine behave the another way. So we just study these 3 things the same way. If we know one thing, we know everything about B, C, and N. Make sense? And then if we know O, we know the F easily. So we study these 2 things different ways. So let's read this. Then let's study boron, carbon, and nitrogen. So I'm just leaving behind oxygen and fluorine. So look the boron electronic configuration. Boron is number 5, right? Boron number 5. Look the electronic configuration of this boron atom. That is 1s2, 2s2, and 2p1, like this. Make sense? So you see this is full, right? 1s2 is full, right? 1s2 is full. So you don't have to do this one. Don't worry about 1s orbital. And this 2s is also full. 2s2, right? So don't worry about this one. You don't have, if you want to show, you can show 2s2, but you don't have to show. It doesn't do anything because both are full, and so we don't have to do. So we are only interested about this unfilled orbital. Make sense? You can do 2s and 2p You can make all. You can make all like this. So I can make all. Let's say let's make all at first. So I have this boron atom, and I have this boron atom. So atomic orbital of boron, atomic orbital of boron. So first of all, I have what? 1s. So you could put 1s here, and you could put 1s here like this. So how many electrons here? 2. 1s has 2. How many electrons here? 1s has 2. Now these two interfere, and one guy goes down and one guy goes up like this, right? Like this. And then this one and this one and this one like this. So this is bonding, this is anti-bonding. How many electrons I have? 2, 4. So I'm going to put 4 electrons here. 1, 2, 3, 4 like this. So this is bonding, this is anti-bonding, anti-bonding. Anti-bonding. So here is 2, here is 2. So you really don't have to show this one while you draw it. Yeah. Now let's look about the 2s. So for boron, 2s is here. Another 2s is here. So this is 2s. This is 2s for atomic orbital. Now they will. How many electrons here? 2. How many electrons here? 2. So you are going to interfere these 2. This is constructive interference, and then you are going to make one line here. So this is destructive interference, and you are going to make line here and like this. So this is anti-bonding. Make sense? So how many electrons here? These 2 come here and sit here. These 2 go here and sit here. Again, you see that this is bonding, this is anti-bonding. So this cancel this one. So you really don't have to draw those because they are already filled. And 2, you see here, 2 minus 2 is 0. 2 minus 2 is 0. They are all paired. So you really don't have to show. Yeah? Make sense? So if they are filled, I mean, they work that way. If you want to draw, it's okay because they work that way. But you really don't have to draw those things. Now let's work. So the P. So I am only concerned with this guy. So this guy is right here, high energy. This guy is high energy here. How many P orbital we have? We have Px, Py, Pz, right? Three sheet, right? In P we have 3. So you could write 3 sheet. 1, 2, 3. Here also 1, 2, 3, like this. And then we will combine this one different way here. So I will show you this one. Here I just erase this board, and I will show how to combine those P orbitals. Make sense? Good. So 1s and 2s I don't have to show. I'm just trying to show that's 2p. So this is filled. I'm not really interested in those. You can draw. Now the p orbital. So I'm only interested in this one, and I have 3p. This is px, this is py, this is pz. This is p in the same level. So this is px, py, pz. So this is 3 orbital. Yeah. So although you see 2p, p means we have px one sheet, py another sheet, and pz another sheet like this. Make sense? So this one is px, this one is py, this one is pz of boron. Either boron, carbon, nitrogen, same thing. You can write a carbon there, you can write a nitrogen there. This is boron here. Now this is also px, this is py, this is pz. So how do they interfere? So in boron, carbon, and nitrogen, so they interfere like this. So these 6 from these 3 and these 3 interfere like this, and they form 2 orbital here. When they constructively interfere, they give 2 orbital here, and these 2 orbital they give the name pi 2p. Pi 2p. This is also pi 2p. This is also pi 2p. Make sense? So then they also they give another orbital here. They give this name as a sigma 2p. Sigma 2p. Because this is coming from the 2p, so sigma 2p. Now above this one, so these are below this line, right? And now above is these 2. So pi star 2p. So this is called pi star 2p. So this is also pi star 2p. And all the way up is here is a sigma star 2p. Sigma star 2p. Like that. So they interfere, and then they give this thing here. So they calculate and they do like this, and they give the diagram like this. Make sense? So this is coming from the constructive interference of 2. This is also constructive interference. This is coming from the constructive interference. These two are coming from the destructive interference. This is also coming from the destructive interference, right? Constructive interference meaning like this, to pick. Destructive interference means like this. Make sense? Now, so this diagram is for what? Boron, carbon, and nitrogen. You are writing always 2 here, 1 here, below this line, and 2 here and 1 here. Always for boron, carbon, and nitrogen. Make sense? Now let's look electronic configuration of. Let's fill the electron for boron. So these are atomic orbital. These are also atomic orbitals. So how many electron here? 1, right? So 1. So this is 1. I can put somewhere here 1 here and 1 here. So where should I put these 2 electrons? The lowest one. So this electron goes here and this electron goes here, like this, 1 by 1. You need to put like that. That's a boron. Apparently our book does not discuss the boron, but it looks like that, yeah? Good. That's a boron looks like this. Make sense? Good. You cannot put 2 electrons here. So since these one and these one are same level, we need to fill electron 1 by 1 first, right? Good. Boron looks like this. Now let's talk about the same diagram for nitrogen. Our book doesn't discuss about the boron. Let's talk about the nitrogen. Or let's say our book does not discuss about boron and carbon. It discuss about the nitrogen. So let's talk about the nitrogen. Nitrogen here, this is nitrogen atom, and this is also nitrogen atom. So everything. So if you look the nitrogen, it looks like this. So this is nitrogen: 1s2, 2s2, 2p3, right? Hydrogen, helium, lithium, beryllium, boron, carbon. Nitrogen is 7, 2, 2, 4, 47, like this, right? This is, so I'm not interested to show this one, and I'm not interested to show this one. They are already filled, right? So they will cancel as I told previously. So 3 electron I'm going to put here, 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 like this. And those 3 electrons I'm putting it here. So this is one nitrogen, this is another nitrogen. So I'm trying to build nitrogen in nitrogen bonding. Make sense? Now put 1 by 1. So I have 1, 2, 3, 4, 5, 6 electrons. First put 1 by 1, right? And then pair, start to pair like this. 2, 4 are gone, right? Now put 1 first. This is 5, but I have 1, 2, 3, 4, 5, 6. So put another one here like this. Make sense? 6 electrons. Now let's calculate the bond order in nitrogen. So bond order in nitrogen. Calculate the bond order in nitrogen, N2. So this is one N, this is another N. So I have, so these are molecular orbital here, these are atomic orbital, these are atomic orbital. Now let's see here, bonding in nitrogen. So what is the bond order? Bond order in nitrogen. So how many bond order is equals to number of bonding. So you see, this is bonding, this is bonding, this is bonding, these are anti-bonding, these are anti-bonding, right? So number of electron in bonding minus number of electron in anti-bonding. There are no electron in anti-bonding above this level. So 0. So there are 2, 4, 6 here, 6 in bonding and 0 in anti-bonding. And divide by 2, that is 6 by 2 is 3. So the bond, how many bonds between nitrogen and nitrogen atom? There are 3 bonds in nitrogen and nitrogen atom. So nitrogen is always like this, N like this. Make sense? Any question? Easy, right? Now, is it a paramagnetic or diamagnetic? You see, there are all the pair. There is no unpaired electron here, right? If this is no unpaired electron, its property is diamagnetic. So if you put the big magnet here, this is a North Pole, South Pole, big magnet here, and hang some nitrogen molecules here, it is repelled by this magnet. That is away by this magnet. This is diamagnetic. Why it is diamagnetic? Because there are no unpaired electron. Pair, but there is no unpaired electron. But if you look the nitrogen atom here, unpair. Instead of N2, if you are filled with the nitrogen atom, they have the unpaired electron, they will be pulled by the magnet like this. Make sense? Good? So nitrogen molecule, this molecule, it has 3 bonds. So all electrons are paired like this. So this is a diamagnetic. It's repelled by the magnet. So I will give this kind of diagram, and I will ask: is this molecule, nitrogen molecule, is diamagnetic or paramagnetic? Just look here, 2, 4, 6. This is pair. So since this is pair, there is no unpaired electron. So this is a diamagnetic. So it is repelled by the magnet. Make sense? Let's look here and here for the property of the N2. This is for N2. So this one is for N2. This is for N. This is for N. Yeah. Any question here? I think it's good. So this is first. So we just finished. What did we finish? We finished boron, carbon, and nitrogen. And I told you our book does not discuss about boron and carbon. So you are just interested with the nitrogen, right? Now I teach you oxygen and fluorine, and we are done for the whole of this course. So now we talk about the oxygen and fluorine. So what happens in oxygen and fluorine, this diagram? So if you look at oxygen, the electronic configuration looks like this: 1s2, 2s2. So this is number 8, right? Oxygen is number 8, right? 1s2, 2s2, 2p. How much? 2p hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen. So 1, 2, 3, 4, 5, 6, 7, 8. So like 2, 2, 4, 4, 8, like this, right? So this is oxygen atom, right? So this is full. So this is 3 sheet: p, 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 px, py, pz. So 1, 1, 1 electron here. 1. Then you make 4. So 2 are here. So 1, 1 in p. This is px, this is py, this is pz. So this is already full. I'm not concerned about this one. This is already full. I don't care about this one too. Yeah. So I only care about this unfilled orbital. So like this one. This is from one oxygen atom. So this diagram just that's oxygen. So this diagram, if you see here. This diagram here, this sigma 2 comes down and this 2 pi 2 goes up. So what happens is I just erase this 2 here and make like this. So this is sigma 2p and this is pi 2p. Pi 2. You see the difference? You see the difference in nitrogen and oxygen? Just previously I was writing this two line here and this line up here, but now I just reverse that. That's the difference. Make sense? So people try to explain. So they go to the laboratory and measure some property, and then to fit with those properties, they try to do the correction in their diagram. Make sense? So the property of oxygen can be only explained by this kind of diagram. If you put this 2 down here and this up here, probably you cannot explain the property of oxygen. Make sense? So they just repeat here. So that's the difference. Now let's put how many electrons I have here with oxygen. So exactly same here. So this is not nitrogen. I'm working with the oxygen now. This is oxygen atom, and this is also atomic orbital of oxygen. Atomic orbitals of oxygen. Atomic orbital of oxygen. Yeah, 2 atoms. Now this is oxygen molecule. This is oxygen molecule. So that's molecular orbital, this one. Now this is sigma 2p. This is pi 2p. There are pi is always 2, and then we have pi star 2p, and we have sigma star 2p. So this one is same for all, but for nitrogen, boron, carbon, these 2 were down and this was up. But in case of oxygen and fluorine, this one is down and these 2 are up. That's the difference. Did I make it clear? Yeah, so it's very simple. Now let's fill the those electrons. How many electrons are here? 2, 1, 2, 3, 4. So let's put one by one first. 1, 1, 1. And you can put this 1 electron anywhere in any seat here. I put it here. Yeah, you can put here, or it doesn't matter where you want to put. And then here, like this. So another oxygen atom also has 4 electrons in outermost orbit. Sorry, in the p orbital, and 2, 3, 4. Make sense? This is one atom. Now I'm going to fill this electron in this molecular orbital. How many here? 1, 2, 3, 4. 5, 6, 7, 8. I have total of 8 electrons, right? Now I'm going to fill them one by one first. So this is the lowest one, so I put 1. And I need to pair this one. So I pair, so 2 are gone. Now I put 1 by 1 here, according to Hund's rule. So 1 by 1 here. Now I need to pair this one, like this. Now how many gone? 2, 4, 6 are gone. How many I have? 1, 2, 4, 5, 6, 7, 8. 2, 4, 6, 8. I have total of 18, right? 8, and I already put 2, 4, 6. Now I need to put 2, right? So where does the one go here and one go here? We have to put 1 by 1 first. And then if we have extra, I would pair this one like this. So this is the oxygen molecular orbital diagram. Make sense? Now let's calculate the bond order. Bond order. Bond order. How many bond form between the 40, 10 minutes. I have 10 minutes. I think we will be done with all class today, and we just discuss in next class about the exam. Yeah. Now like this. Now let's talk about the bond order in oxygen. Bond order. So how many in bonding? 2, 4, 6. So below this are 6 electrons. So there are 6 electrons there. And how many above? In anti-bonding there are 2. And then you have to divide by 2. So 6 minus 2 by 2 is 4. 4 by 2 is. So between the two oxygen atoms. So this is one oxygen atom, this is one oxygen atom. If they bond together, they give 2 bond there. Make sense? There is a two bond between 2 oxygen atoms. Yeah. How many were in nitrogen? Nitrogen were like this, 3, right? But in oxygen we have only 2 bond. Make sense? Now let's look about the. Is it diamagnetic or paramagnetic? Look here. This is pair, this is pair, this is pair. But this is unpair and unpair, right? See unpair electron. So when the electron is unpair, it is a paramagnetic molecule. Make sense? So meaning that if you have a big magnet here at North Pole, South Pole, and fill this with the oxygen molecule, and hang it here, and they are attracted toward this test tube is attracted toward the nitrogen. Make sense? So this is a paramagnetic. Oxygen is a paramagnetic. How about previously in nitrogen? If you put nitrogen here, there were no unpair, right? So it was repelled by that magnet. Make sense? Did I make it clear? Pretty simple, right? So it's oxygen. Now let's look one for fluorine. So that's this is oxygen. This is oxygen. I'm done with the oxygen here. So oxygen molecule is paramagnetic. It is attracted by magnet because there are 2 electrons coming toward unpaired electron, and those electron work as a unpaired electron work as a magnet, and they are attracted toward the magnet. So it's called paramagnetic. So you will see something like this in the exam, yeah. So now let's look at the fluorine, that fluorine molecule. So everything looks same except the number of electrons. Everything looks same here. Everything looks same. All this diagram looking exactly the same. Make sense? Because it's oxygen and fluorine behave the same way, right? Now fluorine. So let's draw the electronic configuration of this one. Fluorine, one fluorine atom. So fluorine is number 9. So 1s2, 2p, 4. I think it's a 5, right? 2p5. Make sense? That's a fluorine, right? So like that. Now how many? So if this is full, I don't pair this one. This is full, I don't pair this one. Now this is only not full. P6 is a full. P5 is not full, right? So P is 3 seat here. 1, 2, 3 seat here. This is PX. This is PY. This is PZ. P is 3. So 3 seat, meaning that. So I have 5 electrons. 1, 1, 1 first. 3 are gone. So 4, 5. So 2p5 looks like this. Make sense? 2p5. Now I'm going to put this 2, 4, 5 electron here. First I put 1, 1, 1, 3 are gone. Now 4, 5. Make sense? Now another fluorine. So this is fluorine atom. This is atomic orbital. Atomic orbital of atom. These are also atomic orbital of another fluorine atom. And this is how many? 2, 4, 5 also here. 1, 1, 1, 2, 2, 4, and is one is unpaired like this. Make sense? So I have how many electrons here in P? So 2, 4, 5, 6, 7, 8, 9, 10. So I need to put the first 10 electrons here in these orbitals. So the seats are already ready here to put them. Make sense? So constructive interference, constructive, destructive. Yeah. So first I put 1. Here is a 1 seed. This is 1 seed. So I put 1, and then I need to put another 2 pair. So this is done. 1 seed, 2 electron. No, maximum 2 electron. How many seeds here? 2 electron. Now put one by one first, and then start to pair it. This set can have 2. This set can have 2. How many gone? So 2, 4, 6 are gone. But how many I have? 2, 4, 5, 6, 7, 8, 9, 10. I have 10, and I just finished 6. Now 2, 4, 6 are gone. 7, 8. 2, 4, 6, 7, 8 are gone. Now I need to put 2 here like this. First one by one, and then we pair, right? You see here, 2, 4, 6, 8, 10. 10 electrons are gone. So 2, 4, 5, 6, 7, 8, 9, 10. So this 10 electron I distributed in the oxygen molecular orbital. There are no electron to put here, right? If I have the electron, I would put here one first, and then would pair here. But there are no more electron I have, right? Now let's calculate the bond order. So bond order is how many in bonding? So below this line, right? Below this line is a bonding molecular orbital. So 2, 4, 6, 6 are there. And how many up above this line? 2, 4, right? So 4 like this. Now and I divide by 2. So that's 6 minus 4 by 2 is 2 by 2. So 1. So the bond between fluorine and fluorine atom is only one bond. Like, make sense? Did I make it clear? It's very easy, right? Now, how about the magnetic property? We don't look here. We don't look here. Look here. Is this pair? It's a pair. It's a pair. There is no unpaired electron in the molecule, right? So this is diamagnetic. So if you hang the fluorine, if you hang this, take a big magnet here, North Pole, South Pole here, very big magnet, and put some fluorine molecule. I'm not talking the atom of the fluorine molecule. And then hang it like this, and would it be attracted to the magnet or repelled by the magnet? It will be repelled by the magnet because no unpaired, pair. Make sense? So fluorine is diamagnetic molecule. It is repelled by the magnet. If I have look the fluorine only, so if you have the F atom here only, it would have one unpair here, right? And it would be attracted to the magnet. If you have the F atom, it would have an unpaired electron here, and it would be attracted toward the magnet. But since F2 molecule, so F2 molecule, all electrons are paired, so there is no possibility of the that molecule being as a magnet and is being repelled. Diamagnetic. Make sense? We are done. So that's it. Yeah. So so this course is done. So there is nothing more to study in this course. Yeah. So there is, I put a slide 21 and 22. If you want to look those, but you really don't have to. Yeah. So that's what you need. So I just want to write this a little bit different way. Sometimes these orbitals are written like this: sigma 2p, then pi 2p, and this is also pi 2p, and this one is also this pi star 2p. This is pi star 2p, and this is sigma star 2p. They also sometimes in the book they write like this way. So meaning that these two guys have same energy. These two guys have same energy here. Make sense? So this has the lowest energy. So the lowest energy. These two guys, pi 2p, these have same energy level here. So I write 2 here, pi 2p, and then these two, this sheet and this sheet, pi star 2p has same energy. So we write like this in the same level here, and this is pi star 2p is the highest energy. So sometimes they also write like this in the book, so don't get confused. Make sense? So we are done with the class, and hopefully you understood something. And this is very important. If you take the chemistry in future, these things are will be helpful. So in the next class, I talk about the exam, the final exam, and the third exam. And I think Friday we don't have to come to class. I will sit online, and if you have any question, you can ask me on Friday. Yeah. So we don't meet Friday on site. Great. Thank you, everyone. So hopefully you enjoy the class already. So I'm going to stop this one.